Let's start by building some intuition. All right, so one of the classic types of machine learning problems to solve is a classification, where in this space, we are trying to train a model that neatly separates these blue dots and these orange dots. Now, what we're doing here is choosing which features we want to feed into the model that will output, that will, like, if this is orange, this means that everything in this space is classified as being part of the orange class, and this is all blue class. So let's just like run this very basic model, and it works nicely. Very quickly it learns that there is a linear separator here. Now let's try it with something more complicated, a little bit harder to separate linearly. Alright, here, ring of orange outside, blue in the middle. Nope, definitely not working here. It's saying here that given these two features, the best performing model will just call everything orange. So that's a no-go. If we were building a machine learning model, this would be the time to do some feature engineering. So x1 squared and x2 squared, let's add these as derived features into our model and see how we can do. Great, there we go. Nicely, this model now nicely separates this blue space from the orange spaces. Now what about something that is even harder? Take a look at the spiral, for example. Now, intuitively, you can already guess that you would never be, no matter how much you train, how long you train for, you will never build a model that can nicely linearly separate these orange classified orange space versus blue space. So the training loss is like garbage for this model. If we did some feature engineering, would we be able to do it? Not really. In fact, the training loss is even worse than the training loss with x1, x2. Even if we added a ton of features, this would still not really work well for us because this space is not nicely separable. So let's add some layers here. Just a couple hidden layers here, a couple of neurons. Shows how many we want, as many as we want. Let's see. Let's maybe add a couple more layers to that even. Let's give that 8, 6. Looks like something interesting is happening here. And there we go. Given all these features, this neural network is able to nicely define a separation space there. Alright, but we are using quite a lot of derived features. What if we just fed it x1 and x2? Would we be able to get to the same place? Something's happening. And our model is exploring. So while that's running, let me tell you a little bit of what's going on here. Every epoch represents a full training iteration, a full training cycle around what iteration dataset. Over here, you can see a nice spark line showing the training loss, where the smaller this number, the better your model is at classifying. If you see these weights here, you get a sense of the weighting of data as it flows from one layer to another and generates our output space here. This is all happening inside of TensorFlow.org, playground.tensorflow.org, which is also linked. It's a very nice browser-based demonstration of how neural networks outperform with standard machine learning classifier ideas. And now at about 2000 epochs in, if we can hit pause on this, you'll see that the neural network has been able to define a pretty nice boundary here. What's really cool about this is that when you implement a neural network, they are not manually defined by a human. You do not like program this. You really just tell a TensorFlow convolutional neural network, okay, I want 3 layers. Each layer I want how many neurons, and you just feed it your raw data. The crazy thing about deep learning is it's able to induce non-linearities into a model. It reduces your need to do feature engineering. You can get a lot out of a deep learning model with very minimal or even no feature engineering. And the results here are pretty impressive. So let's take a look at this now mathematically.